Many applications in computer graphics and geometry processing require the ability to locally orient objects or patterns in a given domain. The local orientations and effects shown here were provided by a symmetric second-order tensor field, which you now visualize using superquadratic glyphs. In this work, we introduced a system by which tensor fields can be designed in tetrahedral volumes. Our user interface consists of visualization options, tensor design options, and a graphical display. The user can view the domain interior by adjusting a cutting plane. We provide two methods of visualizing the field. The first is superquadratic glyphs. In addition, the user can visualize the degenerate curves. There are three types of glyphs in our system, one for each class of traceless tensor. Linear tensors, shown in green, have two negative and one positive eigenvalue. Planar tensors, shown in red, have two positive and one negative eigenvalue. In both cases, the saturated band circles the eigenvector corresponding to the eigenvalue of unique sign. Neutral tensors have one zero eigenvalue and two other eigenvalues that are equal in magnitude but with opposite sign, and so both bands are drawn. There are four types of degenerate curves: planar trisector and planar wedge, linear trisector and linear wedge. We now adjust the viewpoint so that the planar curves are parallel with the camera direction. As we move the cutting blade towards the camera, we see that the eigenvector patterns around the degenerate curves are consistent with those found in 2D tensor fields. We now clearly see a wedge and a trisector pattern exhibited by the middle and major eigenvector fields. If we reorient, we see that the same is true with the linear curves and the middle and minor eigenvector patterns. We now demonstrate the efficacy of our curve editing interface. The user draws a 2D curve on the cut plane. Once sketched, the curve can be modified using simple Bezier deformation. This is a wedge curve, as can be seen from a different viewpoint. The user can deform the original planar sketch from multiple viewpoints to obtain virtually any 3D curve. By hiding the TET mesh, we can see that the system places tensor values at the vertices of a neighborhood around the curve. By using currently off-screen controls, the user can edit the properties of the curve, such as rotation or the tensor mode. Once the desired constraints are set, the tensor field can be filled in for the rest of the volume. If we show the degenerate curves, we see that a linear wedge curve appears where we place the constraint. In addition to the curves that we placed, unspecified curves will also appear. As the user continues to place constraints, these unspecified curves can become more and more prevalent. We also allow the user to design a volumetric tensor field using a 2D tensor field on the domain's surface. These 2D tensors can be converted to 3D using the surface normal as the third eigenvector. Finally, using the tensors at the boundary vertices as constraints, the field can then be propagated into the interior of the domain. If we then detect the field topology, we can see that the degenerate curves form a skeleton of the model. Our system also offers the ability to smooth the field in a local user-selected region. Starting with this field on the sphere, the user paints a small thin region on the vertices exposed by the cutting plane. Once painted, this region can then be dilated to achieve a torus-shaped region that encloses the wedge and trisector curves. We apply local smoothing only in the region selected by the user. We can see that this has the effect of canceling the wedge and trisector curves. We can use our tensor field design system to orient element syntheses. We designed a field on David's head and synthesized tubes along the medium eigenvector's hyperstreamlines. Although the result is interesting, some of the degeneracies cause unwanted disruption of the field's global pattern. Our final contribution is the topological editing of degenerate curves of an existing 3D tensor field. After detecting the degenerate curves, we can perform a sequence of operations to improve the field. We remove a degenerate loop, reconnect two open degenerate curves by selecting the desired sections of the curves, remove an open degenerate curve, and deform a degenerate curve by selecting and modifying a section of it. We apply further topological editing operations to the field until we are satisfied with the result. The improvement of the element synthesis result shows the strength of our topological editing operations.